Okay, so next, let's look at serial and parallel communication. So in a word, these two are very easy to understand concepts. Serial versus, means that data is transmitted one bit at a time. As indicated in this diagram, you can see there's only one data line, and then this bit is transmitted sequentially from input to output, starting with B0 and then B1, so on and so forth. And parallel is quite the opposite. You have multiple data lines, and then everything is, in this case, sending the other way around from out to in, but all the bits 0 to 7 are sent via multiple lines at the same time. Metaphorically, just like whether you choose to drive in a one-lane country road or you want to build a multi-lane highway. So naturally, maybe these two images biasing you, you naturally prefer to drive on a multi-lane highway so you can increase the throughput of your traffic. But in reality, there is other consideration that needs to be in place in order to choose between serial or parallel. Parallel communication, of course, in theory, is faster, but the cost is that it requires more wires, which is not, unfortunately, not something that's always available for embedded systems. You can count how many pins you have on a microcontroller, and imagine if you want to implement a parallel communication mechanism, how many peripherals can you connect to and communicate to at the same time? So that's why choosing serial communication is actually a more practical method to address the needs to have multiple peripherals connected to a limited number of pins. If you are still not convinced, you might say, well, why not just adding more pins or adding more wires? The first reason to hesitate about doing that is you're gonna increase the size of your embedded devices, and not to mention the complexity you add to your overall systems. That said, both serial and parallel communications existed in the development, in the history of embedded system development. Can you think of any examples that any serial or parallel communication examples in your everyday life? So let's look at serial communication, which is much more common, but we choose something that's a little out of date. I'm not sure how many of you have actually seen this guy. I'll be surprised and impressed if you did see one of those, because I don't think they really existed anymore in the slightly modern computers. So this is called a male D subminiature connector. It was invented for the IBM PC compatible computers. And the symbol here is the serial port symbol. And there are more examples of from what I call it an extinct PC, because any PC with these ports exists, then it must be old enough to not even be functioning properly. So the couple of these serial ports we talked about, this guy, this guy, and this guy. and this guy. VGA looks similar, but it's different. It's different protocols. And your USB is also another example of serial ports. We're going to talk about that. And PS2 are very specific for keyboard and mouse. So we saw a lot of these RS-232 used for COM ports, and the PS2 for mouse and keyboard. So in comparison, when you search for parallel ports, you probably wouldn't find many examples. One of the very few examples being this DB25 connector, often used for a parallel printer port on IBM PC compatible computers. It's originally known as a parallel printer adapter and designed pretty much primarily to operate printers. Well, the reason for you might want to think about, so why in this case, why did they choose to use a parallel versus as opposed to a serial port for printer? So why using all the other RS-232 and keyboard and mouse adapter in serial, but using a parallel for printer? So I'm going to leave this as a discussion question. There is no definitive answers. I don't think they really documented the design rationale. Anyway, feel free to think about it, and think after that you can try to search on the internet and see if you can find the designers or the manufacturer behind this parallel port connector to see if they have any accounts on whether they chose the parallel communication. I think either way, it would be a great discussion topic on Piazza. So here is another example from the Nintendo company. This gaming console controller is also using a parallel adapter for communication. Yeah, so the remaining question is to think about why for these printer connector adapter, why did they use parallel instead of serial communication? Another question to think about is when you're communicating serially, what the receiver actually is looking at or monitoring is a wire. And then the question is, how does the receiver know, let's say after you send the receiver a packet, the receiver is going to monitor wire and there's going to be currents flowing through the wires. So how does the receiver know when a packet starts and when it ends? Which is going to be confusing if you send multiple packets or if multiple senders sending multiple packets. How does the receiver figure out how to segment the signals into different packets at its end? So there needs to be some sort of agreement or rules for the receiver to do that in order to actually make sense of the received data. So one actual example here is, this is probably what the receiver sees at its end, a number of 0 and 1s, and there needs to be some way to tell the receiver that where exactly does an actual packet start. So there are two ways to do that. You can do it synchronously, which means you will have a clock wire. A clock wire is basically saying, all right, so here, assuming that this is the data line, and then I'm gonna have another clock line. So the clock line, I'm gonna synchronize the signal with where the data starts. So I can say whenever I have a clock edge rising, this is where the data starts. This is the bit where we start reading data. So it's a very simple mechanism, but it illustrates the idea of using a separate line as indication of where the packet starts. So it's very good for simple ICs because sometimes these ICs, they don't necessarily have their own clock crystal. So it will rely on maybe a master device or the microcontroller's clock to supply these signals through a data line. So it can synchronize with the master or the microcontroller. SPI and I2C are two such examples that rely on clock line to synchronize the receiving of data. Then another method is called asynchronous serial, which means there's no clock wire. Instead, I'm going to rely on special bits in the data wire in order to make sense of when the data starts and ends. So I'm going to look at a more explanation how this works. And one example of this mechanism is UART. So all of these ISPI, I2C, and UART will be discussed later in this lecture. So how does asynchronous communication works? So there are a couple of specialty bits. For example, mark or idle bits. So for example, in this case, mark or idle bits is the 1 bit. So this bunch of ones indicate that there's really nothing to be read. And then the stop bit signals that there is data. And then there is an agreement that after the stop bit, I should be looking for certain fixed number of bits that will come next, which meaningfully indicates some information. So back to this example, here 0 is the start bit. So after a bunch of ones, if the receiver sees a 0, that means, hey, I'm gonna start reading data after that. So there's a bunch of extra payload here. And after that, there is another extra bit called parity bit, which is used to detect potential errors during the transmission. Basically, by comparing the parity bit and the actual payload, you can detect whether there has been error in transmitting the payload or transmitting the parity bit. If either of these suggests an error, then you probably discard this frame and send back some acknowledgement to the sender saying, please send it again. Something is distorted or messed up in the process. And finally, there's a stop bit. So here, this one is a stop bit, which is the opposite of the stop bit. In other words, if you, after the parity bit, if you see another 0, that means there is a packet immediately following this one. If you see 1 after the parity bit, then you should stop reading. All right, so here the question is not about stop bit, it's about parity bit. So there probably needs more explanation to understand how it works. So parity bit, one way to define it is to say, okay, if you read a 0, that means there should be even number of ones in the payload. Otherwise, if you read 1 in the parity bit, there should be an odd number of ones in the data frame. So based on this rule, what does it say here? This parity bit here. So let's count the number of ones in the payload. There's 1, 2, and 3. There's 3 ones, so that's an odd number. That means the parity bit should be 1. But it's 0. Okay, so that means either this payload is corrupted or this parity bit is corrupted. In either case, the best practice is for the sender to tell that to the information back to the for the receiver to send an acknowledgement to the sender asking to resend this packet. So there are a few follow-up concepts about serial communication. We're not gonna discuss these concepts in details. The only requirement is that you know what it means. So for example, full and half duplex. Full duplex means both parties can send and receive data simultaneously, versus half duplex means at a given time is a one-lane bridge. So have you ever driven to a one-lane bridge and then you have to stop and see if there's a car coming? If there's a car that's already coming on the bridge, you're not supposed to fight for the usage. You're supposed to wait until the car passes, and then you can use the bridge to drive to the other direction. So the same for half duplex. Not saying it's only one direction, but it's saying at a given time only one directional transmission is possible. Master versus slave is, you can think of it as a way of defining the relationship between the different ends of a serial communication. One of them being the master device, which has control over the communication with the others, such as it would decide when it is reading or writing to the slave devices. These master devices usually have some sort of a master clock signal, which will govern how the behavior of the rest of the slave devices. In comparison, if some relationship is not master versus slave, it's very likely to be point-to-point or peer communication, which means each device is of equal relationship with the others. Multi-drop, multi-point, and point-to-point, very simple concepts. Point-to-point means you have one transmitter and one receiver, but which is not very scalable if you have multiple devices or multiple components. So multi-drop means you have one transmitter and then you can drop off data at multiple stops at multiple receivers. And then the final design or architecture is multi-point, in which case you have multiple receivers and multiple transmitters. So more case studies for serial communication. We've seen this before. If you remember what this port looks like, the mail, the sub-miniature port using the RS-232 or recommended standard 232 protocol. It's one of the most commonly used protocols for serial communications in various serial ports. Later, it was superseded by USB, and then USB becomes pretty much the de facto standard for serial communication in many uh, computing devices. IS-232 historically was designed for communication between modem and typewriter. So that suggests how old it was when it was invented. And no computers were considered at that time, just typewriter and printer. It, you can say the need for these standards, you can say, predated the need of personal computers. And USB later took over. It's short for Universal Serial Bus. It even has an international organization dedicated to managing such a protocol. It's thought of as an industry standard that establishes specifications for a lot of things, for cables, connectors, protocols, and that are used for connection, communication, and then power supply even between personal computers and their peripheral devices. It's designed and maintained by multiple tech companies, initiated in 1996. So far, there has been 3 generations, 1.x, 2.0, and 3.x. Something you probably use a lot these days, or you talk about these days, is USB-C. And Apple computers are now only providing support for USB-C, at least for the laptops. And a lot of the mobile devices are also transitioning to USB-C. So what is USB-C in this development of USB? We didn't mention it anywhere here, right? So what is it? Is it 1.x, 2.0, or 3.x? Well, just to clarify, USB-C is not so much the protocol, but the type of adapter, or the physical design of the USB protocol. That means, as you can see, let's go back to this slide. In this case, this is, I couldn't see what's inside here, but I'm gonna guess it's a USB 3 point something. So that's the protocol. So on this end is the conventional USB port, but on the other end is USB-C. So USB-C commonly occur together with USB 3.x, but it's the you can say the shape or the size of one of a port or adapter. More precisely, this adapter, not a port. Is the size and shape of the adapter rather than the underlying protocol. So if USB-C is just about the shape of the connector, then what is USB 123? It turns out it's both the software, that means how data is transmitted, and the hardware. So depending on which 123 you are using for USB, the adapter might have different physical design. USB 3 is encouraged to use blue to differentiate itself. And there's also some interesting design here. So the 2 rows of pins on top of this blue receptacle. And the first row contains 4 pins. is for compatibility to 1.x and 2.0. And the second row here is the actual USB 3 pins. So there is this interesting design that includes backward compatibility. So USB transmission rate increases significantly from generation to generation. From the 1 point something Mbps to 10 Gbps in the latest protocol. And you can see from the example of transmitting a 25 gigabytes HD movie, if you use it at 1.1 protocol, it's going to take 9.25 hours versus 35 seconds if you use USB 3.1. Does this remind you of something? It seems to be related to what we talked about, Nelson's law. It's about how the user's internet speed increases by certain percentage every certain period of time. It's again a similar pattern compared to Moore's law. And here you can see almost near exponential increase from generation to generation. Let's take a closer look into USB, because it's a great example to think about serial communication. USB is called host-centric. It's a similar concept to master-slave. Means all the transactions are initiated by the host device. The top level construct is called a pipe. Think of it as once you connect, let's say, your laptop computer and your Arduino board, it creates a pipe that is persistent, that always exists as long as the two devices are physically connected. So it will persist between these two devices to maintain communication. And then so that's pipe. And then the second level is called a transfer. The transfer is an isochronous in same time. It's an isochronous transfer that sends real-time data, such as audio, video, images, etc. And underneath that is something called a transaction. A transaction contains elements of what you want to transfer of a specific type of information. And then there's more. So underneath transaction, you have packets. So here's the data you want to transact, but it's not everything you have in the transaction architecture or the transaction construct. You have something called a token. A token packet defines what to expect from this transaction. Basically saying, what is this about? For example, so this guy says it's about, the foreign data is about setup. And this guy says foreign data is the general I/O information. And then you have the data, the actual payload. And the last piece is a status packet. For example, the status packet could provide information that indicates an acknowledgement or an error correction. So far it looks like we are peeling onions or taking our Russian dolls. You have pipe, transfer, transaction, and then packet. But we're not done yet. So there's even more to talk about. For example, so here's a control transfer, what a control transfer looks like. For example, the control transfer will be used to set up a USB device. The control transfer contains 3 transactions: setup, data, and status. And then each transaction contains the 3 components we talked about: setup, data, and status. So here, there are at least three ways of using the status packet, which indicates different things. ACK, acknowledgement, means that the receiver acknowledges receiving error-free packet. And NAK is the negation of acknowledgement. It means receiver cannot accept data, or the transmitter cannot send data. So it can come from either the receiver or the transmitter. And then store means the endpoint is halted. It could be the receiver is busy receiving data from elsewhere, or being busy processing the data that it has no capability of receiving new data. So the last layer we're going to go into is what's in a data packet. So inside each packet, token, data, or handshake, you can further divide the bits into a number of categories. Sync is a way of synchronizing clocks between transmitter and receiver. PID is simply the identification information. And then if you need addressing, that means you are writing the data to a certain register, or cache, or memory positions, then you need to provide the address. You also have this additional flexibility for addressing, NDP, and then the actual data. And the CRC bit, or bits, for cyclic redundancy check is similar to a parity bit for error checking. And then something to signal the end of a packet. All right, so this is the lowest hierarchy, or the inside-most layer we have built so far through the different layers of USB protocol. Okay, so let's take a step back and look at the whole USB thing. Is it synchronous or asynchronous? And there are 2 ways to look at this problem. First, if it's synchronous, you need to be able to see a clock line or a dedicated wire that accompany the transmission of data. But we didn't see anything like that. So far, we only see one transmission pipe, and there's many other inside layers, but there's no presence of a separate clock wire. And then if you see this kind of a synchronization data structure, it's also a sign of asynchronous communication. Because it's asynchronous, it needs these synchronous bits to help them synchronize, because there's no shared clock information. So in conclusion, USB is asynchronous serial communication.